You are watching Chalkdust, a channel for the mathematically curious. This afternoon, we have a series of special programs celebrating the release of Chalkdust issue 12, available at chalkdustmagazine.com. Coming up, at 2:30, we have The Joy of Colouring. Make sure to have your paper, ruler, pencil, and colouring pencils to hand so you can join in with the drawing and colouring at home. Then, at 3 o'clock, we have The Poetry Show, where this week our team will be looking at how a six-sided dice and a bit of mathematics can help you write your own poetry. But first, we have a program paying homage to Colin Beveridge's article in issue 12. It's time to head over live to Studio 3 for Countdown.
Hello, good afternoon, everybody, and welcome to this special Chalkdust issue 12 launch party edition of the Countdown Numbers game, inspired by, of course, Colin Beveridge's article in issue 12. So this whole afternoon, we're going to be celebrating some of the articles in the latest magazine, and hopefully you've managed to get yourself a copy already. Chalkdustmagazine.com is where you can find the PDF. Lots of exciting stuff inside. So if you haven't had a flick through already, and I hope you have, because a lot of the exciting things that we will be doing over the next hour and a half come from this magazine. Colin Beveridge's article asks this question of the famous Countdown Numbers round. He asks, if you have these 6 numbers which you place on the board, how many possible numbers can you get to from these starting 6 numbers? Well, thankfully, Colin adds a TLDR to the front page of the article. He says, from these first 6 numbers, there are 974,861 distinct answers. The good news is that we're not going to ask our 3 contestants today to find all 974,861. In fact, all we want them to do is to find one correct answer. So let's go ahead and meet our 3 contestants for today. Our first contestant is James Arthur, a mathematical communicator from Cornwall. Hello, James.
Hello.
Thank you for playing with us. There's been a lot of chat today, James, about BidMaths on Twitter. So tell me, out of the 6 letters and therefore 6 operations in BidMaths, which is your favorite?
Indices.
Indices, excellent choice. Good, thank you. Our second contestant today is Belgin Seminolu, a junior data scientist and Math Blaster expert from London. Hello, Belgin.
Hello, Adam. It's a pleasure to be here.
It's a pleasure to have you on with us, Belgin. So in the top 10 column of this issue's Chalkdust, we ask, what are the top 10 mathematical places? So Belgin, I thought I would ask you, what is your favorite mathematical place?
This is a good question. So a few years ago, I went to Paris, and in one of the museums, I saw Foucault's pendulum. So maybe I would say Paris.
I think Paris has some really good mathematical museums. I was very impressed with what they have there when I went over. Thank you, Belgin. We'll have a chat about your mascots later, because now it's time to chat to our third contestant, Goran Newsom. Hello, Goran.
Hello, live long and prosper.
Thank you very much. So Goran is a maths graduate who enjoys pure maths and volunteers at the RI's maths masterclasses. So given that you like pure maths, Goran, I thought I might ask you, what is your favorite theorem?
Oh, all the isomorphism theorems. I love isomorphisms because it's like random thing here, random thing there. Oh, look, they're connected. And it's like, when I first learned it, absolutely blew my mind.
Amazing. I mean, I'm afraid that's the wrong answer. The correct answer is Pythagoras' theorem, but they're also excellent theorems. So thank you very much for joining us. And of course, we wouldn't be complete on our game of Countdown Numbers Countdown without our very own maths genius. So say hello, everyone, to Sophie McLean. Hello, Sophie.
Hello.
So Sophie has wrangled the numbers and the games for us. And so Sophie, you'll be taking us through the solutions because there are some interesting twists, aren't there, to today's games?
There are indeed. We thought this is Chalkdust, this is special. Why will we stick to the standard countdown when we can have a bit of fun?
Absolutely. So we're going to see what some of those twists are as we go. But we're going to start by playing some more conventional rounds. So we're going to start with a conventional countdown round, and then we're going to go on to onto some of the more exciting rounds. So going back to our board, let's ask our contestants to pick a board. So you're going to get to contestants. We're going to ask you to pick a board. So you can see there are 8 choices along the top. 1 large, 5 small, 2 large, 4 small. You see how it goes. So James, would you like to pick one of the 8 boards from along the top, please?
3 large, 3 small.
3 large, 3 small. Excellent choice. Let's head on over there. So 3 large, 3 small. Let's see what we are in for today. So 3 large, 3 small. We're going to have the number 4, the number 5, number 3, 50, 100, and 75. Now, I thought just before we start the clock, Sophie, you might want to remind us what the rules are for this game. So,
Yes.
Sophie, if you wouldn't mind talking us through those.
So for this game, what you've got to do is make the target number using all the numbers at most once. You don't have to use all of them, and the operations of addition, subtraction, multiplication, and division.
Lovely.
And hopefully we won't be having any Bob Mass issues in this game.
Well, who knows? All right, the target is, everybody, 665. You have 30 seconds and some royalty-free music. Off we go. Lovely, thank you very much. That's 30 seconds. Time is up. So let's see how we got on. James, what did you get?
I've got 650.
650, Belgin?
Haven't quite gotten anywhere yet.
Nowhere yet, good. And Goran?
I got 635, but I think that's a bit too far out.
Okay, so James, you're closest. Let's hear your 650.
Yep, so I did 5 times 100 to get to 500. And then 3 times 50, which add them both together, you get 650.
All right, so I'm going to, let's see, Sophie, we should be able to see you a little bit larger now. So 5 times 100 is?
500.
500.
Yeah. Then 3 times 50
Is 150.
150. Add them together.
Add them together and you get 650.
Unless I've made a maths mistake. No, yeah.
No, confirmed.
All right, that's our closest. Let's see. We have an argument in the chat. We have Samuel suggests 100 minus 5.
Okay. 100 minus 5 is 95.
95. And then if you take 3 plus 4 and add them together.
Yeah, 3 plus 4 is 7.
And then, Sophie, tell us what we have to do.
And then multiply, and we get the 665.
665.
Well done, Samuel.
Well done, Samuel. Excellent. A win for the chat, but James gets closest, so that's that. Lovely. All right, so that's, hopefully you're feeling a little bit warmed up now. Time to go back to our board of choice. So let's see, everybody. It's now going to be Belgin, your turn to pick. You get to pick a special game. You get the choice of P, M, or G.
I guess I'll try P.
P. Excellent choice. Lovely. Okay, so here are the tiles for the P game. We have 2x, x minus 3, x minus 2, 3, x cubed plus x squared plus x plus 1, and x to the 4 minus 1.
So yes, in this game, you are allowed to use addition, subtraction, multiplication, and polynomial division. The P obviously standing for polynomial, to try and get as close as you can to the target polynomial. Good luck.
Thank you very much, Sophie. I will just put the board back up because the target polynomial is x squared minus x minus 1. I hope everyone enjoying the PowerPoint 97 sound effects. So this time, yeah, good. We've decided that 30 seconds is a little bit too short, so we're going to give you 1 minute and 40 seconds. Sophie, do you have any last minute advice?
Last minute advice, I'd say this is possible. We have checked this, so you can do it. And yeah, good luck, I think.
1 minute and 40. Good luck. Here we go. And that is it. That's 1 minute 40. You can see that our 30-second countdown clock has become a 1 minute 40 countdown clock. You know, we've just scaled seconds appropriately. I mean, it's just a non-dimensionalization. We do it all the time. We've had an excellent question, which is how are we going to judge closeness? What's the metric for closeness to the polynomial? Well, I think we're just going to use the canonical measure. What do you think, Sophie?
I would agree.
Excellent, good choice. Right, let's hear. James.
Glad we cleared that up.
Yeah, good. James, what did you get?
I think I've got x squared negative x negative 2.
Excellent. So that seems close. Belgin?
I'm a bit off. X squared minus 4x.
Okay. And Goran?
I think I've got it. I think I've got x squared minus x minus 1.
All right. Goran, take us through your...
And everything's frozen. Oh, no, it's fine.
Yep, take us through.
Hang on.
The excitement. Sophie's poised with the board.
Okay, can you hear me?
Right.
Because my thing is going a bit
Yes.
slow.
We can hear you, Goran. People on the chat are showing off. So let's. Excited. So we see who's got it in the chat. We have high.
Okay,
high
I'm gonna
scores.
just go through my calculations. Hopefully you can hear me.
We can hear you. Goran.
So I begin with x to the 4 minus 1 divided by x cubed plus x squared plus x plus 1 to give x minus 1. Then I multiplied that by x minus 2 to give x squared minus 3x plus 2. And then I added on 2x and took away 3 to that. And I think
So add 2x gives x squared minus x plus 2. Take away 3 gives x squared minus x minus 1. Correct.
Oh, fantastic.
Now, as a note, those of you at home may have a different solution. There are, in fact, 2 ways of calculating this one. So well done if you spotted both.
Sophie, do you want to tell us do you remember what the other solution is?
Yes, I do remember what the other solution is. However, I lost my whiteboard rubber for a second. So it starts the same way. We carry on with x to the 4 minus 1 divided by the x cubed plus x squared plus x plus 1 to get x minus 1. I'm not going to actually write the whole thing out because there's not much space, but we have x minus 1. Then x minus 1 plus the 3 gives x plus 2. X plus 2 multiplied by x minus 2 will give x squared minus 4. Difference of 2 squareds for those who are fans. And then from x minus 4, what we do is we take the x minus 3 and add the 2, subtract x minus 3, and that gives us x squared minus x minus 1 as well.
Lovely. Thank you very much. All right. We get a next selection on the board. So we're going to ask Belgin, this time it's your choice of the special game. So we've played. Oh, wait, no, I asked you last time, didn't I?
Right.
Goran, your turn. You get to pick between our 2 remaining bonus games. So you get to pick M or G.
cool. Let's go for M.
M, excellent choice. Let's have a look what M has in store for us. Okay, so the tiles are the matrix 1 minus 1 1 2, minus 3 2 minus 1 4, 2 0 0 2, 1 1 0 1, 0 minus 1 0, and just behind the scorpion's hand, the identity matrix 1 0 0 1. So while you're writing them all down, Sophie, do you want to tell us what the rules are for this game?
Yes, so for this, you are allowed matrix multiplication, addition, and subtraction. We're not allowing division on this one, as much as I'm sure you'd love to calculate inverse matrices right now. That's not going to be in this 100 seconds.
Excellent. Okay, so that's our board. The target is, he says, 1 4 minus 4 0. You have once again 1 minute and 40 seconds. Off you go. And there we go. Good. That's time. That's your 1 minute and 40 seconds and some lovely royalty-free music by Kevin MacLeod. Lovely. Okay, let's see what you got. James, how close did you get?
I've got a mixture of matrices on my page, all equally far away from the target matrix.
Excellent. Good. Belgin?
My matrices are quite far away as well. The best is -1207. I don't think that's close enough.
How is that the best? What's the worst?
The next
I
one
got
I
the
got
zero
had some
matrix.
massive numbers.
Oh, that's good. Goran, you got the zero matrix.
I ended up getting 0, -1, -1, 2, and a lot of regret for picking M.
Excellent. Good. All right. So maybe we should just jump to Sophie and find out how this could be done. Sophie, tell us how.
So, I mean, I'm really surprised no one got this. Like, it took me about 10 seconds, you know. So you start with the 2002, which is twice the identity, as you might have noticed, and multiply that by 1101, which gives 2202. To this, we take -3 to -14 and multiply it and subtract from it, the above, which gives us -5, 0, -1, 2. Now we take this and we add to it 1, -1, 1, 2. Adding together gives us, I'll write it over here, -4, -1, 0, 4. And these numbers might be starting to look a bit familiar, because then if we multiply this by 0, -1, -1, 0, we get our answer. 1, 4, -4, 0.
Well done, Sophie. Easy. Trivial. Exercise
Come
for
on,
the
guys, up your game.
Yeah.
You toying with us?
It's okay because there's one fun board left to play, so we'll play that now. This is the exciting G board. So here is what it looks like, contestants. So we have a 90-degree anti-clockwise rotation around 0, 0. A 180-degree rotation about -1, -1. An enlargement scale factor 2 about the center 0, 0. A reflection in the line x equals 3. The translation 2, -1. And then a nice one to finish, a translation 1, 0. Now, we're going to start with this. And Sophie, do you want to tell us the rules before we reveal the target?
Yes, so this is obviously a simple game now. What you have to do is work out which of these operations and the order in which you should do these transformations in order to get from this starting triangle to the end on the graph. And I would like to now just say congratulations to Angela Brett, who managed to work out that G stood for graph.
Excellent. That's
Wait,
the sort
which
of
triangle are we starting from? Which one are we ending at?
We are starting at this, and the target Adam is just about to reveal. Ta-da!
you have once again 1 minute and 40 seconds. Off you go.
Go.
Oh, God help us. So you go from there to there, and you've got 4 steps. Oh, Gordon Bennett. Let's just pick a random ones. Let's just do 180.
There we go. I mean, why don't they use this music on the real show? That's what I want to know.
They're going to be watching this, and you'll see some changes in the next series of Countdown, I'm sure.
All right, let's see how close do we get. James, you first.
I've got a spattering of triangles all over my page, all equally far apart from the end triangle.
Good. At least you're consistent. Belgin?
It's been turned around, it's nowhere near.
Good. Goran?
I've got it, but not fully written down.
Oh, okay. Goran, let's hear your solution then. So we get your board
Okay.
out.
So I began...
I'm not going to attempt to draw this. Imagine it.
I wouldn't expect you to. I began with a reflection in the line x equals 3.
Okay.
And then a rotation of... Oh, hold on. Hold on a minute. No, I think I've gone wrong.
Oh,
I think I've gone wrong right at the start.
That is a shame.
Can I make a guess? Is it all of them? And it doesn't matter which order you do it in?
That would have, I wish I had written the question so that was what it did, but unfortunately not.
Sophie, put us out of our
Right.
misery.
So first, you rotate 90 degrees anti-clockwise about the origin. And then you translate with the column vector 1, 0. You enlarge it the scale factor 2 about the origin, then reflect in x equals 3, and then do the final translation by the column vector 2 minus 1. If you want to have a go at home, this should be available on YouTube for longer, so you can listen again and try for yourself.
Fabulous. Thank you very much, Sophie. So the final scores then, because coming up next, just to give you a teaser of what you're going to enjoy in a few minutes' time, we have the Joy of Colouring with Florian Bouillet. That's coming up next. You can enjoy, so make sure you have your pens and some paper and a pen and your colouring pencils. And we're going to construct some interesting designs like you can see all through issue 12, and then we're going to colour them in. If you haven't managed to print off the back cover of the magazine, we've tweeted a link so you can go and print it off very shortly, because we'll be doing some constructions. But that is the end of our little countdown game. Our final scores are James has 1, Belgin is yet to score, and Goran also has 1. So nice and conclusive. I think that's all good. So thank you very much for playing. Excellent. So it's going to be goodbye from James.
Goodbye.
Goodbye from Belgin.
Goodbye.
Goodbye from Goran.
Bye-bye.
Thank you very much, and goodbye from Sophie.
Goodbye.
And it's goodbye from me. Goodbye.
You're watching Chalkdust, a channel for the mathematically curious. You're watching a special afternoon of programming to celebrate the launch of Chalkdust issue 12, available at chalkdustmagazine.com. The cover of issue 12 features some very interesting geometrical constructions, part of which has been coloured in. In our next program, we will take a closer look at the meaning of these constructions, so have your pencils, ruler and paper ready, and be ready to relax as we discover the joy of colouring.
Hello, everybody. Welcome back. And we're extremely lucky today to have Florian Bio. Florian, say hello.
Oh, thank you very much for inviting me here.
It is an absolute pleasure to have you with us. So Florian has constructed all these excellent designs that you can see in the magazine. And here is indeed the back of the magazine, which we've left uncolored in for you so that you can enjoy this during this session. Florian's going to construct some designs for us in the spirit of coloring for mindfulness. And while he's doing it, he's going to tell us a little bit about how he started doing this and what he was thinking. So if you have any questions for Florian, drop them in the chat and I will pass them on to him. But Florian, it's all you.
Okay, cool. Thank you very much. So yeah, I'm going to try and show how you end up with this picture that looks like quite crazy. And it all started with a simple triangle, and it all started with an equilateral triangle. So I'm going to start by drawing an equilateral triangle of side length 8. So I'm going to use a trusty ruler and measure side length 8. And then I'm going to quickly use a compass to work out the rest, how to draw the rest of the triangle. So you won't be able to see, I am doing the compass bit in pencil because I don't want it to actually appear in the end of the drawing, but you should maybe see vaguely what I'm drawing. So in case you don't remember, to draw an equilateral triangle, once you've started with one side, in this case of side 8, then you just draw at each point a circle of radius 8 on both endpoint, and the two circles will intersect at 2 points, in this case here and here. And I'm just going to start drawing this equilateral triangle. Now, this drawing kind of came with the idea of something called the logarithm spiral, which you can read a bit about in the Chalkdust issue 12. But it's a spiral. I don't like drawing curves myself. I only like drawing a straight line. And there's a way you can draw it by only using straight line. So here we're going to draw a 3 logarithmic spiral that's going to kind of spiral inside the triangle. And I'm only going to do it with straight line. And the way you're going to do is at each stage, I'm going to measure a tenth of a way away from a vertex and draw a new triangle. So it'll be easier if I show you. So we're starting with a side length 8. To take away a tenth, I'll need to measure 0.8 or measure 7.2 because I prefer doing 90%. So 7.2 is here, so I'll mark a dot at 7.2. I shall mark a dot at 7.2 on this side as well. 7.2 is about here. Hopefully you can follow me at home and you'll end up with the same picture. I'm going to measure that way because of stuff being in the way. Up 0.8. Here. And once I've drawn this, I'm going to link the 3 dots together to make another triangle. So then we have a triangle within a triangle. Right, now let's repeat it again. In case you want to work a bit faster than me, hopefully this is readable. It says the length, so first I started with 8, then I measured 7.2, now I'm going to measure 6.48, which is a bit harder to measure on a ruler. But you know, you can be a bit more rough and say 6.4. That's 6.4. 6.4 is roughly here. And 6.4 is roughly here. And again, I shall now just join all of these together. Right. That's something kind of pleasing and just kind of doing something repetitive. Kind of, yeah. I mean, that's what mindfulness is, kind of paying attention to what you're doing. And there's something kind of repetitive here that's just nice and calming. Okay, so as I said, I did the calculation beforehand, so I don't have to do them again. The next length after 6.48 is 5.83. 5.8, this is getting closer and closer. Yeah, up. 5.8. Let's do modulo 20, so 25.8. Again, leave that together. And if you're at home doing this along, feel free to later tweet at Chalkdust your drawing. As you can see like it's already starting to spiral in, and it's going to be kind of this curve that I'm drawing that's going to end up being the spiral. So 5.83, 5.25. This is where it's getting harder and harder to draw. And 5.2. You can go as far as you want, but I'm going to stop after 8 iterations. So after 5.2, 4.7. And then we'll change to actually coloring it stuff in, which is also the easiest bit. 7. 4.7. There we go. Right. I think I'll stop here for the moment because I want to show how from one triangle you can kind of go quite far and you'll see kind of a nice spiral coming, but it's kind of nice then to add more and more triangle to end up with the kind of pictures I've actually got in issue 12. So I've got a triangle here. I can then attach to it a second equilateral triangle by using the same idea here. I'm just going to draw the outline of the different shape I would consider. Would help if I draw this a bit further. So one triangle here, a second triangle here. Good. And on this triangle, here I've gone, I guess, clockwise away around the thing. Here I'm going to do the other direction. So if I measure, it's a 7.2 here, and I measure 7.2 here, and I measure 7.2. Would help if I actually measure 7.2. Got confused with the direction. And if I measure 7.2 here, and do this time the triangle kind of going slowly rotating in the other direction. And I repeat that for a bit, something kind of nice is going to happen around here and around here. I'm not going to repeat this now because I would like to do the coloring because this is the mindfulness bit, but at least you can see how to construct these should you want to construct them by hand. Should you not want to construct them by hand, as has been mentioned, there's a few examples of these in Chalkdust. There's a few examples as well on my site that's all been constructed by computer, which you can just then easily print to color yourself. So what I'm doing here, I'm drawing 6 triangles next to each other, because we know that 6 triangles can all meet at one point. Okay, and 6 triangles also form a hexagon. So I'm kind of constructing a nice hexagon here, which then gives you the idea, oh, what if instead of a triangle, I draw a hexagon next to one of these triangles. So let's also have a look at what would happen there. So up. I can construct therefore 6 triangles. If I do this pattern in each of them, by kind of keep reflecting, you'll see that it'd be fine that they that the pattern will kind of match together. Okay. And then, yeah, so then the question becomes, what happened if I also then did a hexagon next to it with the same principle? All right. So with a circle, I've got a point here, and I've got a point here. From here, I can then start measuring distance on the circle. One here, one here, one here, one here, up. So I can then just draw a hexagon. Da, 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 da. And again, I could then fill in the hexagon with one of the hexagonal spiral if I measure 7.8 everywhere. And putting triangle and hexagon together, we do end up, surprisingly, with a picture like this once I fill things in. Now, you might not be able to see that we actually have triangles and hexagon here. So before I do coloring in, let me use a spare copy to show you where the triangles are. So I'm going to draw a red line like here. And you'll see there's a triangle here that does not look quite red and outline enough. So let me switch to the black line. There's one triangle here. There's a second triangle here. And if you kind of go around, you'll see there's 6 triangle here. 1, 2, 3, 4, 5, 6. And these are hexagons. So by putting loads of triangle and hexagon with this kind of logarithmic spiral in, you get some kind of nice picture that I can start coloring in. And the beauty of this is you've kind of lost the triangle and hexagon, so that when I kind of do coloring in, I forget there's some triangle, I forget there's some hexagon. I kind of see this like nice little shape here that I'm going to just start coloring. And that is how I kind of tend to relax these days when I've got the time. For quite a few of us, it's been a bit of a stressful year. And I find that coloring in pictures very relaxing. And I decided that, you may remember quite a while back there was a craze with coloring in book, but I found them, well, less interesting to me. I do like something that has pattern. I like something that has geometry. So that's why when I came upon this spiraling logarithmic drawing, I thought, well, that's quite cool. And I also knew about tiling, and this is how I decided, well, what would happen if I kind of combine these pictures from the spirals with the ideas of how to tile a plane. And then some kind of nice pattern started to emerge. Now, I'm not exploring here by hand and paper, but once you start talking about tiling, I kind of then turn my attention to, well, what about tiling instead of in the Euclidean plane? What if I start tiling in the hyperbolic plane? And so then I started drawing some picture where tiling happened in the hyperbolic plane. The reason I switched to added some stuff in the hyperbolic plane afterward is there's something more, there's more can happen. So in the Euclidean plane, it's been known for a very long time that if I'm only going to restrict myself to one shape, there's only 3 regular tiling. These namely being the hexagonal tiling, the triangular tiling, and the square tiling. But as soon as you go into the hyperbolic plane, there are infinitely many regular tiling. Right, green, blue, and yes, you may have noticed I'm going to use the 6 colors, well, 6 rainbow colors, mainly because the 6 triangles next to each other, so I'm going to try and repeat that to have each side be based on a color. So now that I'd like to see where I'm going to go with this. So now that I've done a bit of the center, I'm going to concentrate on the side, and let's concentrate on that side, and let's do the primary color. So I'm going to do a bit of red here. Let's do red and purple on the side. Oops. I wanted that to be red. As I'm not sure about the quality of the video camera and how well you can see, I'm not going to go far too small in all of these. I'll finish those later. Let me start somewhere else. It's just nice to just concentrate on this and think about nothing else. Green, blue, right. Yellow and orange. Yeah. The nice thing about using regular polygon or the Euclidean plane is then you can start cutting them out and make some of the Platonic solids. So I had a bit of fun, for example, making a dodecahedron based on the same principle. And it's kind of just fun to have something to color in and then make a physical object you just have with you and just look at it. Yeah.
Florian, so can you tell us a little bit about the software that you use to?
Oh yes,
to make
yes. Completely forgot to mention that. So these picture I used on LaTeX something called Tick, which is a drawing package. And you draw by defining coordinates and paths between coordinates. So I use some kind of little loop to first, well, a little. I use a little algorithm that just draw a triangle and then a for loop that kind of repeat that triangle, rotating it 90 degree, well, not 90 degree, but rotating a tiny bit and making it a bit smaller. For the hyperbolic geometry, of which I don't have any printed example with me, but there are some examples in the Chalkdust magazine, I use something called Cinderella 2. And actually, those pictures I first produced using Cinderella 2. And Cinderella 2 is a software that allows you to draw a bit like GeoGebra. And in honesty, you probably could use GeoGebra for anything that's Euclidean. But Cinderella 2 also understands hyperbolic geometry. And so there's a mode you can go and say, okay, draw in hyperbolic geometry. So then it will, when you draw a straight line between 2 points, it will curve it in the correct way so that it's part of the hyperbolic geometry. Both of these programs are free. LaTeX is free, and Tick. There's some good example on how to use Tick on something like LaTeX example. I think that's the website I use. And Cinderella 2, if you Google Cinderella 2 math, you'll find the program that you can download for free. The documentation is a bit hard to understand, but I'm always happy to reply to any emails that get sent my way about this thing in particular. Not about the program in general.
Lovely. I like how you describe ticks just so casually, as if it's not just, a toy for sadists. You just like, oh yeah, I just use ticks. It's easy, right? It just works.
Well, okay, yeah, it's not easy, but it's fun to play with. Therefore, it doesn't sound like work.
Yeah. Yeah, I like that part of the job as well. It's like, oh, I'm just going to make it pretty.
Yeah.
This is lovely, and I look forward to seeing everyone's drawings. As you said, Florian, if they tweet them at Chalkdust Mag on Twitter, then we can pick them up and share them. And of course, all of the there are multiple drawings, multiple designs from you in the magazine, and we link to your website as well. But if people Google your name, there are more designs on your website, right?
Yes, yeah. If they Google my name, I think I'm the only Florent Bouillet with their own website, so that should be fine. And there's a few more designs on my website.
Lovely. Well, thank you very much, and a real joy to sort of see some live colour again. I thought I had some real sort of ASMR vibes. Very nice indeed.
Well, thank you very much for inviting me over.
Splendid, Florian. Thank you very much. And all right. Thank you, everyone, for joining in this section. Thank you, Florian. Let's find out what's next.
You are watching Chalkdust, a channel for the mathematically curious. We are enjoying an afternoon of special programming to celebrate the release of Chalkdust issue 12. Next up, it's time for a rhyme in this week's episode of The Poetry Show. Hello, and welcome to The Poetry Show. This week, we're looking at how a simple mathematical idea can help our viewers at home to write their own poetry. But first, we have a poet who is coming on the show to inspire your creativity with the performance of a mathematical poem. So let me welcome to the show, Sam Hartburn. Hello, Sam.
Hi,
Thank you
Matt.
for joining us today. So tell us a little bit about yourself.
Okay, I am a mathematical editor and proofreader in my day job, but I like playing around with the artistic side of maths, so the language, the visual, all that sort of thing. So this is one of the things that I enjoy doing, is making maths rhyme and writing poems about it.
Brilliant. And I believe you have a poem in the latest edition of Chalkdust, which you're going to perform for us today.
Yes, so I'll just share my screen quickly. So just as a little introduction, it's well known that you can't construct a square with the same area as a given circle using a ruler and compass, but I didn't know until I happened to read about it that you can construct a square with the same area as another polygon, and I thought that was quite cool, and so that is what I wrote a poem about. So here we go. So I had this circle, but I wanted a square. Don't ask why, that's my affair. The crucial aspect of this little game is that the areas should stay the same. Ruler and compass are the tools to use. It's been proven impossible, but that's no excuse. Many have tried it, but hey, I'm me. I'm bound to see something they couldn't see. So here we go. Oh, that's a rectangle. Never mind, I'll give it a try. Call the long edge X and the short edge Y. Now make a line to form Y plus X. From the midpoint, make a semicircle next. Extending Y to that arc gives the length I desire. I can prove it with algebra if you require. Draw a square on that side, and I don't want hysteria, but the square and the rectangle have the same area. But what about the circle? So here we go. Oh, that's a triangle. Never mind, I'll give it a try. If I find the midpoint of any side, I can draw a right angle up from there. It's a crucial ingredient for a square. A parallel line through the third point now. Fill in the top and the sides somehow. It's a rectangle, same height, half the base. And that means it takes up the same space. And I can already square a rectangle. But what about the circle? So here we go. Oh, that's a pentagon. Never mind, I'll give it a try. If I join the corners between pairs of sides, I can make it into triangles, 1, 2, 3. And squares from triangles are now easy. Put two sides together, joined at right angles. Then by some famous theorem involving triangles, the square on the long side sums the other two. Repeat the process and then we're through. But what about the circle? So here we go. Oh, that's a hexagon. But come on, for 6 sides, I know what to do. And the same will work for 7 too. This is easy. Look, it's great. I can even do the same for 8 and 9 and 10 and... Holy cow, that looks a bit like a circle now. In fact, I've got it. It's obvious in it. To square the circle, you take the limit. The practical details of the construction I'll leave as an exercise for your deduction.
So I'm going to give you a virtual round of applause, Sam Hartman, for that fantastic poem about not squaring the circle.
Thank you very much.
So thank you very much for coming on the show today. I've a few questions for you before we look at how our readers can make their own poems today. So as well as writing mathematical poems, you also write mathematical blogs sometimes.
I do occasionally, yes. I have a blog, samhartburn.co.uk.
Yeah, so when you come up with an idea, do you sit down and decide, I'm going to write a blog today, or I'm going to write a poem today, or do you kind of find an idea and it just becomes a poem or becomes a post?
Probably more it just becomes a poem or becomes a post. I'll usually have an idea in my head that I'm mulling over, and I'll be playing around in GeoGebra or just on pencil and paper, or while I'm walking to school, things like that, just mulling ideas over, and they might form into a post or a poem, or whichever happens to best suit it.
Brilliant. And have you written many other mathematical poems?
Not that many. I do have another one in Chalkdust in the previous issue, which was all about Kepler's barrels. There are a couple of other poems on my blog, but yeah, only a few.
So maybe our readers could look forward to maybe another poem in issue 13 or 14.
I'll see what I can do for you.
Okay, wonderful. Sam, thank you for coming on the show today. So we'll be hearing again from Sam shortly, but now we're going to take a break from poetry to have a look at some of the mathematics we're going to need to use to generate our poems today. So to explain this mathematics, we have a second guest on the show, who is Brad Ashley, who is joining us today. Brad, are you there? You are here. So Brad, tell me a little bit about yourself.
Hi, I am a MSc student at the University of Sheffield doing mathematics, and I really like popular maths books, like simple, complicated maths explained simply for fun.
Good. And Brad has come on the show today to explain to us Markov chains, which is a mathematical tool we're going to be using later to generate our own poetry. So before I spoil any more of what Brad's about to say, I'm going to hand over to Brad, who will tell you what Markov chains are.
Nice. Yes, Markov chains. They're this 100-year-old piece of mathematics made by well, they're created by a Russian mathematician called Andrei Markov, surprisingly, that have suddenly become a really important piece of maths with the rise of computers and the computer age. So I could talk about the formal definition and throw big words like stochastic processes around, but they wouldn't really help us understand what's going on too well. So instead, I am going to do a couple simple examples. So if I switch you over, is that all good? Do you see that?
Yeah, that's great. I can see that.
Amazing. So what we're going to quickly do is we're going to make a simple model. We're going to make a model that will predict how we're feeling on a certain day. So to keep it simple, let's just say we have two possible feelings, happy and sad. You can either have a happy day or a sad day. So what we're going to do is we're going to represent them as nodes on the graph, H for happy, S for sad. So now we need some sort of method of transitioning from a feeling to a feeling. So from a happy day to a happy day, or a happy day to a sad day, etc. So let's put an arrow in. And what this means is we're going from a happy day round to tomorrow also being a happy day. So we need a probability for this to happen. So we'll take some arbitrary numbers, but we'll consider ourselves quite optimistic people. So let's say if today is a happy day, there'll be a 5-6 chance that tomorrow will be a happy day. Now, since something has to happen tomorrow, I know it's 2020, we feel like the apocalypse is nigh, but something does have to happen tomorrow. That means tomorrow, if it's not happy, it'll be sad, meaning we'll have a 1/6 chance it'll be sad tomorrow. Okay, so what if we're sad today? We can do the same sort of thing. Let's come up with some new probabilities, and let's say if we're sad today, there's a 50-50, there's a 1/2 chance we'll be sad tomorrow, and then we fill in the last probability like that. So what have we got here? What we have actually created here is something called a two-state Markov chain. Now, what makes this a Markov chain is it's a set of states, a set of probabilities of transitioning between these states, and it has something called the Markov property, which is the important part. The Markov property, what that is the chance of something happening is solely dependent on what happened previously. So, for example, the chance of a happy day happening is solely dependent on the day before the happy day, i.e., the probability of going to a happy day is either this probability from a happy day, meaning it was a happy day before. I said happy day a lot there. It's gonna happen a lot, so get used to that. Okay, so we've made this little model. But what can we do with it? So if we say today is day 1, and let's say today's a happy day. We're having a good day. We're playing with some maths, so of course it's a happy day. We then put a counter on the happy day state, and we can use these probabilities to predict what's going to happen tomorrow, so day 2. So before we do that, we're going to use a dice, and we need to assign the dice rolls to the probabilities. So let's say if we roll a 1, roll a 0, a 1, sorry. If we roll a 1, we'll follow that 1/6 chance round, and if we roll a 2 through 6, then we'll follow that round. You can check the probabilities yourself, or you can trust me that that is the case. So what if it's a sad day? We'll say that even rolls go back round to a sad day, and odd rolls take you from a sad day to a happy day. Okay, so day 1's a happy day. Let's play with this. We roll the dice. Oh. We're looking at these probabilities here. So we've rolled a 3. You see that? So we follow this bit round. Day 2 is a happy day. So what about day 3? And this is where the Markov property is coming in. What's happening on day 3 is only dependent on what's happening on day 2. It doesn't care what day 1 was. Day 1 could be happy or sad. It doesn't matter. It's because day 2 is happy. We're using these probabilities. Okay, so let's roll again. 6, 3 is a happy day. We can keep going. So let's find out how we're going to be feeling for a week. 2, happy again. Been a very good week. 3, happy again. And it's been an amazing week. We're happy every single day of the week. There you go. Okay, so in reality, we're not happy. Well, like, so how do I say this? So we could have rolled a 1 then. Like, we could have rolled a 1, the dice just wasn't. And should we had rolled a 1, we would have followed this round to the sad day, and then any rolls after that would be off these probabilities, because it would be the day after a sad day. Instead, the odds weren't in our favor, and we just kept going around like that. Now, this is a very simple model, but you can see how you'd make this bigger, how you could add more states. So you could add a boredom state and an excited state and as many feelings as you'd like. And then you just add more probabilities. One thing to know when you're doing that is that the probabilities leaving a certain state will always add to 1. It's a good check to make sure you've done it correctly. So the probability of leaving happy here are 5, 6, and 1, 6, which add to 1. So it's a good check that you've made one properly. But that's a very simple model. So instead, well, now we're going to look at a much more complicated one, which I have drawn up because I didn't fancy drawing this whole thing live on air. So let's take 3 simple sentences. I love Markov chains. Markov chains love me. And Markov is I. 3 completely normal sentences that we all say in our daily lives. So what we can do is we can create a Markov chain from these sentences. So if we let each word of these 3 sentences, including the punctuation, the full stop at the end, be a state, we can then derive probabilities from the chance a certain word follows that state. For example, the word Markov appears 3 times in these 3 sentences. 2 of those times is followed by the word chains. Once is followed by the word is. We can then say that within these 3 sentences, there is a 2/3 chance that the word Markov will be followed by the word chains, and a 1/3 chance the word Markov will be followed by the word is. So we can draw this up. We can do this analysis for every single word, including the punctuation in the sentence, and then draw up a Markov chain. So if we just talked about the word Markov, you can see there a 1/3 chance is and a 2/3 chance to change. Notice that we have a start state here, which will become very apparent in a second why we need that to be there. 2 things to notice on the probabilities here is sometimes you have a 1, you have a 100% probability. That's obviously because the word is only appeared once in these 3 sentences, and it was followed by the word I, so there's a 100% chance the word is will be followed by the word I. The other thing to notice is not every single state has an arrow to every other state. So there's not an arrow from the state of start to the arrow to the state of is. Well, this is just because is never started a sentence. In these 3 sentences, is appears once, and it does not appear at the start of the sentence. So the probability here would be 0%. So we could draw that arrow there, but we would just put a 0 in it. So it wouldn't affect what we're doing with it. It would just clutter up the graph. So okay, what can we now do with this? So let me just get this piece of paper here. Give us somewhere to write. Hopefully that is still very readable. Perfect. So what we're going to do now is we're going to put our counter on start. And you can see that I've taken the liberty of pre-drawing up the dice rolls for this. You again can check that those match up, but you can just trust me that they do. And what we're about to do is generate an entirely new sentence. So we're looking at these probabilities. Roll the dice. We roll the 2. So over here, 1/3 chance, 1 and 2. We follow this down here. Our first word is I. All right, well, we keep going. Now we're looking at these probabilities, a half there, odd and even. We got even, so we follow this down to there. Full stop. That's our sentence. Which isn't really a sentence, but that's not the extraordinary bit. The extraordinary bit is this is not one of the 3 sentences we started with. This is an entirely new sentence that we've just generated from these original 3 sentences using this Markov chains model. So we could formalize this. We could take some bits of maths from linear algebra. We use matrices. We're not going to talk about that here because that would just take far too long. But if anybody really wants to have a chat about that, you're welcome to DM me on Twitter. I will happily have a chat. or check out my article in the latest issue of Chalkdust. It explains a bit further what happens there. But this is how we can use Markov chains to generate new sentences. Now, this is a bit of fun, but I'm just going to switch my camera back over now. There you go. Hello. But, so these weren't really, well, that wasn't really a sentence. Full stop isn't much of a sentence, but that was just because the data set we were working from, the 3 sentences, it wasn't much to work from. In reality, in all of English language, the word chains is not followed by the word love half the time. It might be, I don't know the actual probability, but it's unlikely to. But what if instead of 3 sentences, a handful of words, we had 1,000 words or 10,000 words or 100,000 words? We could then, the probabilities would then become much more fine-tuned, and the sentences we could generate were much more likely to be actual, coherent sentences. So this is exactly what people have done. There's a fun little experiment online that someone's created that allows you to generate new Donald Trump tweets from the entire list of his previously tweeted library. And the tweets that generate are eerily something like you'd expect him to say. But like on the more serious side, this is used in a lot of industry as well. So Google PageRank, which is one of the algorithms behind like Google search results, uses, whilst more complex, this sort of analysis. It uses a very more complicated version of a Markov chain, as well as text prediction on your phone. When you've got those predicted words above your keyboard, again, it's much more complicated. There's a lot of amazing programmers and computer scientists going behind that, but the primitive idea is this exact sort of word analysis that we've just done here. And in fact, if you play that little game where you just press the center word continuously and don't press any of the other ones, you've actually reduced their big complicated algorithm almost basically down to exactly what we've just drawn here. Yeah, so I'm by no means an expert of this sort of thing. They're just really interesting and fun to play with. So in a nutshell, that's what Markov chains are. Thank you. Okay.
There we go. We're back.
There we go.
I was unmuting the wrong window, which is why I did not appear.
That's a little off there.
Brad, thank you so much for that introduction to Markov chains. So this is a really cool idea. And as you mentioned, if people want to learn more about Markov chains, we can recommend them an article on the latest issue of Chalkdust by Brad Ashley about Markov chains, which is a really good read and is similar to the talk, but has some more detail for people who want to learn more. But anyone listening to that explanation about Markov chains may have been thinking to themselves, so we can use Markov chains to generate sentences and tweets. Maybe we could use Markov chains to generate some poetry. And this is what we're going to be having a go at now. And everyone watching at home can also join in with this and have a go at generating their own poems. So if you have a 6-sided dice to hand, you have everything you need now to write your own poems. So what we've done for you is, as Brad said, you can generate Markov chains by taking a large collection of sentences and turning them into a Markov chain. So we did this. So inspired by Sam's poem, I took a copy of Euclid's Elements, which is all about geometry. And inspired by the great poet Shakespeare, I took Shakespeare's sonnets, because they're now in the public domain, and I generated a Markov chain based on these two. So now we're going to have a go at using that Markov chain to generate some poetry. So if you head over to this website, you should find the instructions that you will need to generate your own poem. So it has boxes to click on for dice rolls, and you can use that to generate poems. In about 3 minutes' time, you will be performing some of your poems live on the show. Good luck. we are going to start reading your poems out in about 30 seconds. So if you've not finished, finish your poetry. Okay, and welcome back to the Poetry Show. So everyone at home now has had some time to have a go at generating their own poems using Markov chains. And now we're going to be joined by David Sheard and Sam Hartburn, who are going to perform some of your poems live on the show. So David, welcome to the show. Sam, welcome back to the show.
Hi.
Before we see some of your poems you've generated, David is going to perform for us a sonnet and a small piece of Euclid, so you have a good idea of what the source material is. So David, take it away.
Yeah, I have chosen sonnet 130 because it's one of my favorites, and I thought it would only be appropriate to read out Euclid's famous fifth postulate, the parallel postulate. So here we go. My mistress' eyes are nothing like the sun. Coral is far more red than her lips red. If snow be white, why, then her breasts are dun. If hairs be wires, black wires grow on her head. I have seen roses damasked, red and white, but no such roses see I in her cheeks. And in some perfumes there is more delight than in the breath that from my mistress reeks. I love to hear her speak, yet well I know that music hath a far more pleasing sound. I grant I never saw a goddess go. My mistress, when she walks, treads on the ground. And yet, by heaven, I think my love as rare as any she belied with false compare. And in contrast, and that if a straight line falling across two other straight lines makes internal angles on the same side of itself, whose sum is less than two right angles, then the two other straight lines, being produced to infinity, meet on that side of the original straight line, that the sum of the internal angles is less than two right angles, and do not meet on the other side.
Okay, so we've heard a small segment of Shakespeare and a small segment of Euclid's Elements. Now it's time to hear some of your creations. So Sam, have you picked a first poem for us?
I have. I've got a lovely one here. Perfumed tincture of the square on half and a triangular pyramid, is right lines be divided into four triangles. But when it meet and beauty hath thought can be joined, in either fixed circles.
Beautiful. David, do you have a second poem for us?
Sure, yeah. They are proportional to thee, one that we may be parallel to it. Hence the angle, and this proposition is equal to an other. Therefore the sum of youth and gentle verse, and similarly to show how oft as those whose extremities given.
Beautiful. Belonging in any poetry book. Sam, do you have a third poem for us?
Yes, here we go. Extremities of section be turned round through these poor beauties, still for still, called its opposite faces. That sounds like it should have some meaning, if we think about it carefully.
Yes, maybe. Or maybe not, as it's randomly generated. David, do you have a fourth poem for us?
Yeah, quite a short one here. Majesty. Ratios AB, hence AC is equal. Were truer words ever spoken? I think not.
Beautiful. And Sam, do you have one final poem created by our viewers to share?
Okay, one more. This is just a short one. purity with the concave circumference.
Lovely. So thank you, David and Sam, for coming on and reading out those poems. And thank you, everyone, for watching the Poetry Show today. And don't forget to join us next week when we'll be finding out what the integral of iambic pentameter is. Goodbye. You have been watching Chalkdust, a channel for the mathematically curious. This has been a special afternoon of programming celebrating the launch of Chalkdust issue 12. Don't forget to head to chalkdustmagazine.com to read the magazine. It's now time for us to head offline for the night. So now I hand you over to Pages from CFAX. Good night.